Hey y'all, this is the last video for Unit 12. Thank goodness. I'm hoping this one won't be so difficult as last week's stuff. But today we're going to be talking about if you were to take a 2D object, so let's say a rectangle or a triangle or a trapezoid, you were to rotate it around a line or an axis, what shape would be formed, what solid would be formed if you were to rotate it. So the first shape we're going to start with is a rectangle. And this is when a rectangle is rotated about a line. We're going to be looking at rotating it around an X or Y axis. It generates a cylinder. So when a rectangle is rotated around an axis, it generates a cylinder. The volume and surface area of the cylinder depend on the dimensions of the rectangle. And so what I'm going to show y'all real quick, and then we'll do this example. But what I'm going to show y'all is a visual of what's happening here. So here we have this orange rectangle. And if I were to rotate it around this line that's drawn, okay, let's just assume that's maybe the x-axis or something. If I were to rotate that around, it is creating this cylinder. Okay, so where we have those flat lines on the side, when you rotate those around, they're creating those circles on the edges. And so thus this cylinder is created. And so when we look at this first example, it says, what is the radius, height, and volume of the cylinder formed when this rectangle is rotated about? We're going to start with the x-axis. So here's what you want to picture. If this was flipped around the x-axis, what we would have is something like this. And what's happening is as this is rotating around, it's creating these circles on the side, and so we have now created this cylinder. Okay, and so when I count what my radius is going to be this part, okay, because that is where it's flipping around. So our radius here would be 3. Our height is going to be the height of this cylinder, which is going to be this distance in pink, which is 5. And so now if I want to get the volume of a cylinder is pi r squared. So that would be 3 squared times the height, which is 5. Okay, and so that would be 9 times 5, which would be 45 pi. And what you're going to notice over these first few examples is that we're taking the same 3x5 rectangle and we're rotating it different ways. And you're going to see how these answers will change along the way. Okay, and so now instead of flipping that over the x-axis, now we're going to flip it over the y-axis. And so just visualize what this would look like. Now we're going to be flipping it over the y, and so it's going to be coming out this direction. But we still have, if it's rotating around, we still have these circles that are being created on the top and bottom this time. And so now when we talk about radius, our radius is going to be this amount. Okay, because that's going to be half of that circle, half of that diameter. And so here our radius is going to be 5. Our height is now going to be going from top to bottom. Our height is now going to be here, which is going to be 3. And so when we get our volume here, it's going to be pi. Our r now is 5 squared, and then our height is 3. So that's 25 times 3, which would be 75 pi. So notice how our volumes are different depending on which way we rotate it. So why are the volumes not the same? That's what this question asked down here. Well, the volumes aren't the same because we're squaring different numbers each time. So that's why. Nothing too crazy there. Okay, so number 2 says, here we have the same 3x5 rectangle. It's the same rectangle. It's just shifted over. And so if we go around the x-axis, think about what's happening here. We go across the x-axis, okay, and it's just still this cylinder. Okay, it's the same cylinder we had last time we did the x-axis, except it's just shifted over, but it's the same thing. And so this is still a cylinder. Sorry, really bad handwriting, so I'm doing this on my laptop. The radius here, still going to be the same. Oh, I just drew. That's not the radius. Sorry. The radius is here. Okay, so that's still going to be 3. The height is 5. And just to save time here, we've already figured this out. This was 45 pi. So now we're going to do the same thing, except we're going to do it over the y-axis, and this is where this is going to look a little bit different, okay? Because what's going to happen here is if we rotate this around, we're going to have, if I rotate this piece here, if I rotate it over the y-axis, that's going to rotate over here. If I rotate the smaller one across, it's going to rotate over here. So what we have is this big cylinder with a cylinder inside. And so when we're talking about volume, then we really just need to get the biggest cylinder because the other one's inside. So we're not going to count it twice. And so when we get the description here, so this is still a cylinder, and then what we'll say is that there's one cylinder embedded. Okay, so it's inside. We just don't need to double count it because it's just part of the bigger one. Okay, and so the radius then, if I'm looking at the biggest radius would be 3, and the height would also be 3. So when I get the volume here, it would be pi 3 squared times the height is 3. So that would be 9 times 3 would be 27 pi. Okay, so now I would love if those things did not just disappear like that. Here we go. Just want to clear that. There we go. Okay, so now when we talk about the surface area, think about what surface area here would look like. We would have the surface area from part A. Okay, so if we go over the x-axis, so I go over the x-axis with this cylinder, we already have that information. Our radius was 3 and our height was 5. And so when we plug that into the formula, surface area of a cylinder is 2 pi times the r, which is 3, times h, which was 5, plus 2 pi r squared, so 2 pi 3 squared. When you add all of that up, you get 48 pi. Okay, so that's all the surface that's being shown. Okay, and then part B, you're not going to see that cylinder on the inside, right? Because it's covered up by the biggest cylinder. And so we just need to get the surface area of the biggest cylinder. So that would be 2 pi times 3 plus 2 times pi, 2 pi, and then 3 squared. And when you do all of that, you get 36 pi. Okay, so now we go on to the next example where, again, here we have the same rectangle. Okay, so again, if we go over the x-axis, this is not changing. It's just the cylinder has been shifted over to the right from our previous examples, but it's the same cylinder. And so here we still have a cylinder. The radius is still 3, the height is still 5, so our volume is still 45 pi. Nothing new to do there. But this is where things get really fun. So if we go over the y-axis, okay, think about how far this line right here is from the y-axis. So if I rotate it over, we're going to look more at rotations next unit also, but that's 1 away from the y-axis. And so if I rotate that over here, it actually looks like this. Okay, so what we have here is we have, again, if we're rotating a rectangle, it's still going to be a cylinder. Okay, so still a cylinder, except notice what's on the inside. Another cylinder. And so we have this big cylinder, but we have a hole in the middle, a cylinder hole in the middle. And so we have a cylinder with a cylinder hole. Okay, and so if we look at the big cylinder, Okay, so the big cylinder, if you look how far away it is from the y-axis, that's 6 units away. Okay, so our radius here would be 6, and the height would be 3. Okay, and so if I plug that into the volume formula, that would be pi r squared h. So pi times 6 squared times 3. Okay, and that is, I think it's 108. Hold on, let me double check. Yeah, 108. Okay, so that's the big cylinder, but we need to subtract out the smaller cylinder. Okay, so I'm going to subtract out whatever the smaller cylinder is. So the volume of that would be pi. Our r, our radius of the small cylinder, is going to be 1 squared, and the height is still 3. So 1 squared is 1 times 3, so volume is 3 pi. So if I take 108 pi and I take out the cylinder inside, then our volume would be 105 pi. Okay, these say graph the line, or given the lines in the x interval, graph and shade in the area formed. Find the volume of the shape rotated around the given axis. Okay, so on number 4, we have y equals 3. Okay, so that's the koi here. That's going to be a horizontal line at y equals 3. Okay, and then we have y equals 0. So again, another horizontal line, y equals 0. And then we have, it says the interval, he also says something that says x-axis is less than 4 y-axis. Okay, I think y'all's note says something different here. I think it doesn't say the second part. It says between 0 and 3. So between 0 and 3 would be in between here and here. Okay, so notice what you have. You have, it's actually a square, right? Because every side's the same. But let's just use our same rules as the rectangle. And so if we rotate this, I think that y'all's notes say rotate around the x-axis. This says y-axis, but I think y'all says x-axis only. So if we rotate this over the x-axis, it would look something like this. And again, when you rotate this rectangle, it's going to form a cylinder. So our radius here would be 3. Our height here is also 3. Okay, and then so when we get the volume here, that would be pi 3 squared times 3, which would be 27 pi. Okay, we're actually going to come back to, actually, let me go ahead and talk through B, and then we may not come back and work it, but it'll make more sense after you learn the triangle here in a minute. Okay, and so here we have y equals 1/2 x plus 1, so I'm going to graph that. So I'm going to start at 1, and then I'm going to go up 1 over 2. Okay, and this says, it's cut off on my slide, but it says between 0 and 4. Okay, so I'm going to actually stop there with my points because that's right there at 4. Okay, and then it says y equals 0 is the other line. Okay, and so what we have here, if it wants this interval in between, we have this shape here. Okay, and it says to rotate this one around the y-axis. It's cut off on here, but we're going to rotate this over the y-axis. So if we do that, think about what would be created here. It would look like this. Okay, well, we know along the bottom here that that looks like the bottom of a rectangle, right? So this is going to look at like a cylinder. If this was filled in along the top, that would also be a cylinder. So what you have to think of here is that we have a cylinder, but where I'm about to color in green, that place has been cut out. Okay, and what you're going to find here in a little bit is that this is actually a cone. Okay, and so when you rotate a cone or a triangle, it's going to create a cone. And so what we would need to do here is we would need to take the volume of the cylinder and subtract out the cone. So this kind of problem will make more sense here in a little bit when we look through cones. All right, so let's talk about rotating triangles. And again, I'm just going to show y'all a quick little visual of this. So if we wanted to rotate a triangle, okay, you can see what happens here. If this is rotated, let's say this is along the x-axis. Okay, you can see this. If I rotate this, notice what's happening. It's creating that circle on that line that's straight. It's creating the circle, and then it's still got that point up top. Therefore, this cone is being constructed. And so, again, a triangle, when you rotate it, creates this cone. So when this triangle is rotated about the axis, it generates a cone. And then, of course, the volume and surface area will depend on the dimensions of that. So when we look at number 1 here, this says number 5 on y'all's notes. Find the radius and the height of the cone formed when this triangle is being rotated. Okay, so if we rotate it over the x-axis, think about what's happening here. It's going to be rotating over that, and it's going to create this circle on the bottom. Therefore, it's going to create this cone. So if I count the radius here, and this is kind of hard to count, you have to be careful here because you have to notice that this point up here is actually going up to 5. So our radius is 5. The height would be 3. Okay, and volume of a cone is base times height over 3. Okay, so pi r squared is the base. So pi 5 squared times h over 3. Here, these 3's can just cancel, so the volume is 25 pi. Okay, so now, same thing, except instead of rotating over the x-axis, we are going to rotate this baby over the y-axis. And so if I think about flipping this over the y-axis, it's going to look like this. And so we have this cone now where our radius is now 3 and our height is now 5. So when I get the volume, that would be pi r squared times 5 over 3. Now I cannot cancel these 3's out because I have to square that 3 on top. But that would be 9 times 5 is 45 over 3 would be 15 pi. Okay, when we get those volumes, which one was bigger? The x-axis one was bigger. It's kind of bizarre. You think they should be the same, and they're not. Okay, we got a few more to go. So here we look at this triangle. So describe the solid formed when this triangle is rotated. So if you think about going over the x-axis, we would have a cone here in purple. And then the triangle on the left, if I rotate that, we would have this cone on the left. Okay, and they're sharing the same base. So this would be 2 cones with the same base. Okay, and so let's get the radius. Now the radius for both cones is going to be the same, okay, because they share that same base. So the radius is 3. The height of the cone on the left is 2, and the height of the cone on the right is 4. Okay, so if we get the volume of the cone on the left, that would be pi times 3 squared times 2 over 3. So that volume would be 6 pi. Then if I get the volume of the cone on the right, that would be pi times 3 squared, but now the height is 4 over 3. 9 times 4 is 36, divided by 3 is 12. And if you add those two together, you get 18 pi. All right. And so now it's also asking for the surface area. So this goes back to last week's lessons where we have these 2 cones that are connected, this composite. Your surface area here So surface area of a cone is, surface area of a cone is pi RL. Okay, so pi times R. I'm going to do the cone on the left. So times 3 times the lateral height. Okay, the lateral height right now, we don't know. Okay, we know the height. We do not know the lateral height. So I need to find that. So to be able to find that, I'm going to look at this triangle here. So that's going to be 2 squared plus 3 squared is 9. So that's 4 plus 9 equals x squared. So that's 13. All right, so our lateral height here is square root of 13. And then part of that surface area is adding in pi r squared. Now, you can do this now and then take it away later. That's fine. Or you can just understand that the surface of that cone on the left, you cannot see that. It is not on the surface. So I'm not even going to add pi r squared in because it's just going to go away later. So the cone on the left, the surface area is 3 root 13 pi. Okay, and so now if I look at the surface area of the cone on the right, that would be pi r is 3 times the lateral height. And here we do not know that lateral height. Okay, so I'm going to look at this triangle here. Okay, and I'm going to get the lateral height of that cone. Okay, so this one is going to be 3, 1, 2. This one's nice because this is a 3, 4, and then this would be 5 triangle, 3, 4, 5. So our lateral height here is 5. Again, you can add pi r squared, but you're just going to have to take it away because you cannot see that circle because they're connected. And so here, this would just be 15 pi. So if we're talking about the surface area, this would be, it doesn't really matter the order you put these in, but 15 pi plus 3 root 13 pi. Goodness, this is lasting longer than I thought it would. Okay, if we go over the y-axis here, okay, so if we flip this over the y-axis, this one's going to be easier, because if we flip this, 1, 2, 3, 4, if we flip it over this way, and we've created this cone here, this is just a bigger cone with that smaller cone inside, because when we flip over that smaller cone, it's just going to be inside that one. And so this is just going to be still, it's going to be 2 cones, but one is embedded. Okay, and I'm just going to give you these answers, and if you want to pause it and check it, you can. But the radius is 4, the height is 3. I'd want to get the volume of just the big one, because the smaller one is just a part of the inside of that, so I don't need to double dip there. So the volume here would end up being 16 pi. Okay, and the surface area, I'll just talk through it, but I won't work it, is 20 pi. Again, here, the only thing on the surface, if you see my cone in pink, that's the only surface you can see because the purple cone is going to be inside and you're not going to be able to see that surface. And so all here I would have to do is get the surface area of the biggest cone, and that would take care of that. All right, again, I'm just going to kind of talk through this one because this is like earlier on number 4B, I talked you through one like this, so I'm just going to do that again. Describe the solid form when rotated about the y-axis. So here, if I rotated this across the y-axis, it would look something like this. And so what's happening here is along this bottom, I have this circle that's going to be created. And if you think about if this was continued up top, that would also be a circle. And so what we have is this cylinder, but we have this area on the inside here that's not there, that's being taken out. So if you look at what that looks like, that is going to be a cone. So we need to take a cylinder and subtract a cone. The answer here ends up being 160 over 3 pi, but I do not believe we need to go through that. Last two. Here we have a semicircle, and it says the semicircle is going to be rotated around the y-axis. And so I think you probably know what this is going to look like, but I'm just going to show you, is that this circle, if I rotate this around, is going to create a sphere. So we have this semicircle that is going to create a sphere. These are my favorite because these are easy. Our radius here is going to be 3. So if I got the volume of a sphere is 4/3 pi r cubed. And if I do all of that, I get 36 pi. And then surface area of a sphere is 4 pi r squared. And so that is also 36 pi. These just happen to be the same here. It is not always the case. As you probably know by doing other sphere examples, that's not always going to be the case. Last one, we have this is called a quarter circle. So describe the solid form when this semicircle is rotated around the x-axis. And so what you have to think of here is if this is rotated around the x-axis, it's going to look something like so. So what we have here is a hemisphere. So if I count the radius here, our radius would be 5. And if I get the volume of this is a half of a sphere. So I'm going to do 4/3 pi r cubed. And if we do that, we get 250 over 3 pi. That's the easy part. If you remember back to spheres in the last lesson, the volume, we don't really have to think much about that because that's everything on the inside. So not much to change there. The surface area is where we have to think a little bit more. So surface area of a sphere is 4 pi r squared. So that'd be 4 pi 5 squared. So that would be 100 pi. The problem is when we get the surface area of a sphere, we need to cut that in half because that is a hemisphere. But what we're not taking into account is in a sphere, this circle part here was originally not exposed. But now since we've cut it in half, it is now being exposed. So we need to add in that circle that we can now see. So now if I add in pi r, which is 5 squared, I'm adding in that circle, that would be 75 pi. That's why last lesson over spheres, we said to get the surface area of a sphere, it was actually 3 pi r squared. And that's because we can now see that surface.